Hello, over the past year I've been exploring how literate programming can be enriched with refinement types. Literate programming is a paradigm where readable explanations are embedded into programs and can then be compiled to either a target language or documentation. Refinement types facilitate the encoding of basic and complex computation through refinement subtyping. For example, the Boolean type can be seen as a refinement of integer, where the value holds to either 0 or 1. This facilitates more accurate program verification at compile time, but can be tricky to understand. Mapir aims to novelly enrich these two features under a maintainable and understandable guise. For example, the aforementioned Boolean type can be encoded in Mapir as follows. This can be additionally integrated into a function that returns whether or not a numerical is positive. Firstly, the file is tokenized before being passed into an abstract syntax tree. The type checker then converts this into static single assignment form before being able to reason with it. The Mapir type system uses two main contexts. The typing context stores bindings of variables to their explicitly annotated types, and the propagation context stores bindings of variables to their previous assignments. To begin with, Gamma stores the inbuilt type numerical, the defined type boolean, the isPositive function header, and the injected return function, which takes an argument bool. Since isPositive takes a parameter of type numerical, number is of type numerical. Following this, the tlet rule can be used to assert that rv1 through 3 are of type boolean. The doOn rule asserts that if a variable is modified under converging statements, then its refinement can reflect this, specific to the expression in the do block. So, if number is greater than 0, then rv1 is set to 1. For a set statement to be valid, the expression must be a subtype of the assigned target. This is checked using an SMT solver. If it isn't, then it is set to 0. Therefore, the refinement of rv3 can be conditional to this. Finally, the tfuncCall rule asserts that the type of rv3 is a subtype of Boolean. This validates the function. After this, the AST can be tangled into Python code, or alternatively, it can be woven into text documentation. Mapir generates the refinement predicate, a set notation representation, and some example satisfactory and unsatisfactory assignments for the type. Here we have two custom types. 100 asserts that the value must lie between 0 and 100, and 10 asserts that the value must lie between 0 and 10. We have a function that takes 100 and outputs a 10. It does this by dividing the input over 10 and returning this. This is statically verified, as any number between 0 and 100 divided by 10 will be between 0 and 10, so it successfully compiles. However, if we change this value to 8, we will get an error message with an unsatisfiable core. This means the return value could possibly be 11. Numericals are encoded in the numerical pos type, with a refinement that the value must be greater than or equal to 0. Booleans are encoded as before. The function isPositive takes a numerical positive and returns a Boolean. Inside this, a do statement ensures that the input is greater than or equal to 0. If it is, the return value is set to 1, and if it isn't, the return value is set to 2. This compiles. Even though the return value is set to 2 here, it will never be reached, as this statement statically holds true. This would cause a compile time error. Thank you for watching.